So today's our last day, and it is pretty much a review day. I'm going to spend a few minutes going over algorithm analysis for recursive functions, but I'll just do that for a few minutes. Most of today is going to be reviewing for the final. We're going to go over midterm 2, especially the questions that you might expect to see on the final. And then we're going to go over some of the stuff with trees, just quickly, what you can expect. So let me share my screen. And I guess what I'm going to do first is I am going to finish up with the, going to finish up with the algorithm analysis first, and then we'll get into the details of the exam so that I don't talk about the exam first, then get some break where I talk about algorithm analysis and come back to the exam. I will say just quickly for those of you joining late or with questions about the Tennessee Voice, if you fill out or go online and fill out the Tennessee Voice, I'll give you 30 extra points on the lab. And I had a question on Piazza about how that works with labs. So the labs, there's 11 labs. They're worth 1,200 points because one of the labs, I think it was lab 5 with bit matrices, was worth 200. So there's 1,200 points. You're being graded already out of 100 because I, quote, dropped the lowest one, but the way I dropped the lowest one is to just make it out of 100. So what you're going to see to make that happen is eventually I'll make one of the labs worth 0 points. And that will effectively force it to be done out of 1,100. So you can get as much as 1,230 points out of 1,000, and actually that can improve your final grade because while labs are worth 40% of your grade, in fact, because you can get you can get 1,230 if you got the maximum number of points, that you would actually get 1,230 times the 40%. So that would work out more to probably something like 44. So it would actually contribute an extra 4 points to your composite. So it's definitely worth going in and getting those extra 30 points. And then just upload the screenshot showing that you completed it to the Canvas link. And someone asked, what is the website for that Tennessee Voice? And someone chatted it. So if you go to the chat, you should be able to see that link. Okay, so questions about that before we get started. Jonathan, yes, go ahead.
What you talked about was actually the grade for the labs, correct?
Correct.
Wasn't the total amount of points supposed to be 130 points? Or 120?
What do you mean 130?
I mean 1,300, I mean.
So there's 11 labs. If there's, I have to go back and check. I believe that there is 10 labs worth 100 points and 1 lab worth 200. So that would be 1,200.
Yeah.
It's better for you if I graded out of 1,100 than if I graded out of 1,200. That thing I just showed you it's more advantageous for you to have a smaller denominator.
All right.
So, Maximilian, go ahead. Max.
How do you want us to go about training the Tennessee Voice evaluation?
How do I want you to do what? Go about?
How do you want us to like turn it in? Like,
So there's so take a screenshot. It'll give you a confirmation page.
what do we
Take a
submit?
take a screenshot of that, and then on Canvas there's a link. Go to Canvas.
All right. Yeah, I see the thing
Got it? Okay. Under Labs, just upload it to
on
that link.
Canvas.
Yep. You have until next Wednesday. But I forget when it closes, so don't tarry on that one, okay? I'm not sure when they close Tennessee Voice, but I don't think you have forever to do it.
I was able to check the due date in case anyone's wondering. It's going to be the 27th.
The 27th. So even though I said it as the 29th, the last day you can do Tennessee Voice is the 27th?
Yeah, that's correct.
Okay, very good. So it sounds like you have until Monday to do Tennessee Voice. Okay, any other questions? Okay, I'm going to stop the video just to stop any unstable internet connections. And let's just get started. So like I said, I'm just going to spend about 10 minutes or so going over algorithm analysis for recursive functions. And in fact, the book does an outstanding job. So I'm going to just go and bring up the book. And I have to move, if you see my mouse moving around and you can't see not see if you can see my Zoom controls or not, but I'm moving all over the place because I have Zoom controls all over the place. Okay, so the book kind of tries to introduce time analysis for recursive algorithms in a concrete way, which I'm going to do too. So it does it with binary search. I assume everyone can see my screen at this point, correct? Think so? Okay. If you can't, let me know. But at any rate, the big thing about binary search here is they've done it recursively. So you can see that there's a recursive call. And the other big thing is that with binary search, every time you do it, you look at the midpoint, and then you eliminate half of the array. So down here, they say, okay, if the input size is 1, you only make one function call because obviously you only have to look at one element. And if you have an array of size 2, again, you may have to look at all of the elements, and so on and so forth. So for example, let's just quickly look at an array of size 8. There we go. Okay, so we have an array of size 8. So the first place you would look is mid 3. And let's say the value is above 3. So it's in this part of the array. So at that point, you've eliminated half of the array. You only have 4 left. Okay? So in effect, you've done one analysis thus far, or one comparison. You did it on this one. And the number of remaining comparisons is going to be however many are in 4. So you can kind of say, okay, the number of comparisons with T of 8 is 1 plus the number of comparisons that we have left with 4. Okay, so with 4, we again look at the midpoint. 7 plus 4 is 11, divided by 2 is 5. So we're looking at 5. So that's one comparison. So T of 4 is equal to 1. Plus, if it's greater than 5, we have to look at this array, 6 and 7. So it's the time to look, or number of comparisons with 2. So T of 2 is equal to, in this case, 6 plus 7 divided by 2 is 6. So we look at 6. So that's 1. And if it's in the, if it's greater than 6, so it's in the array with 7, it's right here. So it'd be 1 plus T of 1. And finally, T of 1 is our base case. T of 1 is equal to 1. So you could see that it's 1, T of 1 is 1, so that's 1 plus 1 is 2. So since T of 2 is 2, this is 1 plus 2 equals 3. And since T of 4 is 3, this is 1 plus 3 equals 4. And that's how we get the 4 here, but you can also see how we got the 3, the 2, and the 1. But the important thing that you hopefully saw is kind of how you get recursion in general. So for an arbitrary array of size n, it would require this one comparison that we do right here, plus we look at 1/2 of the remaining array. So the remaining thing is plus t of n divided by 2. And if you look at what the remaining time is here, you can see this is a constant. You can see that this is a constant. And you can see this return statement is a constant. And inside the if else, those are constant. They're not constant statements. Inside the if else, that's where you have to do the call to binary search. So that's where you end up with the, essentially, this is a constant plus t of n divided by 2. And that gives us our first result, which is that if you're able to have the input at each point, we call this a recurrence relation. And the solution to it is log n. So in this case, t of n is equal to log n. So anytime you can have the input at each step, you get a log n result. And that's also what binary search trees do. They essentially have it at each point. So if you have a binary search tree, especially an AVL tree that's balanced, at each point when you're doing a find, insert, or delete, it halves the input. So you do one comparison there at the root. So t of n is equal to 1, which is the comparison at the root here, plus the time to do the search in either of the two subtrees, which is t of n divided by 2. So again, you get log n. So any questions about that? If I have any questions here. Okay, in that case, I'm going to move on. So not all, so here we have another one. And in this one, we are going to be looking at a case where, see if they have a, they don't. So here is a case where they're doing recursion trees. I already showed you the call tree once. So here's a call tree where you start with a function, it calls itself recursively, having the input at each step. There are other ones that, sorting in particular, that function a little differently. So I'm just going to give you a quick example. There's an algorithm called quicksort, which you'll see in 302. And roughly speaking, what quicksort says is divide, it basically says for I equals 0 to n minus 1, well, it basically first says, okay, I have an array. I want to sort it. So the way it's going to sort it is it looks at the first element, which it calls the pivot. And what it does is it moves everything that is smaller than the pivot, in this case 2, to one side of the array, and everything that's greater than the pivot, which in this case is 6, 8, 10, and 5, to the other side of the array. And then it puts the pivot between the two of them. So effectively what it does is it sweeps through the entire array and puts things either to the left or right of the pivot, depending on whether they're less than or greater than the pivot. And that takes n operations. And then what it does is it recursively calls itself on each side of the array, which usually, if the pivot's in the middle, is roughly balanced. So you end up with basically n plus 2 times t of n divided by 2, because you make 2 recursive calls, one on the left side, one on the right side, and each of them has roughly n divided by 2 elements. And then in order to partition the array into the 2 halves, you have to look at all n elements, so it's n. So the recurrence is what you see here, n plus t of n divided by 2 plus t of n divided by 2. And here they show you the tree that results. So you do n operations here, then you call 2 recursive calls that each do n divided by 2 operations. And then each of them in turn calls 2 recursive calls that does n divided by 4. So you can see here that at each level, n operations gets performed. And here there's 2 recursive calls. Each of them does n divided by 2 work, so you get n. Here, there's 4 recursive calls, each doing n divided by 4 work, so you get n. And because you're dividing n by 2 at each point, the number of levels right here is log n. So you end up with n log n work. So in fact, that's the solution to the recurrence that you get when you have n plus 2 times t of n divided by 2. And these are the 2 most common recurrences that we work with in computer science. So your sorting algorithms tend to end up being n log n, the best ones, because they operate under this procedure. So that's how you typically end up with either a log n algorithm, you have the input at each step, and each step requires a constant number of operations to each iteration, or each recursive call does a constant number of steps. And the other common one is each recursive call does n steps, normally looking at an entire array, and then makes 2 recursive calls, each of them on half the input, and that results in n log n. Now, just one more thing before we're done here. Sometimes it's not, sometimes recursion looks a bit more like iteration. That's not normally when you would exactly do recursion, but let's see, what's an example of that? A good example is Diamond Hunter or palindromes. Let's do palindromes. So I'm going to now go here, and we want to look at, remember, palindromes what you have is a string, which we make it look like it's an array. So you might have B, R, A, R, B. That's a palindrome. And the recursive definition was that if the string is empty, or of size 1, It's a palindrome. So that's the base case. And then the recursive case is that if the two ends, so if the characters at the two ends of the array match or the string match, and the string obtained by eliminating or removing these n characters, these two n characters, is a palindrome. Then the string is a palindrome. Okay, so in this case, what we have is that for the base case, we know that a moment. I'll extend the page. So we have that t of 0 is equal to t of 1 is equal to 1 because that's a simple comparison. That's a constant. And we have that t of n is equal in effect to that comparison or a constant plus the time to work on a string that is n minus 2. So that is that time. Well, if we look at this one, so let's just go quickly to another screen. So if we look at n, so let's say it was n, and then it calls something that's n minus 2, which calls something which is n minus 4, which calls something which is n minus 6. All we're doing is reducing n by 2 at each point. So let's just do something concrete. 10 would go to 8, to 6, to 4, to 2. And that's equal to effectively 5 calls. So you get 5 calls here. 1, 2, 3, 4, 5. So when you're reducing by 2 at each point, all you get is n divided by 2 calls. So coming back here, this is actually equal to c times n divided by 2, which is order n. So recursion doesn't always give you log n or n log n. If you're not having the input, but instead decreasing it by a constant, then you still end up with order n. So I guess the last thing I'll say about recursion is that if you have a recurrence of the form t of n equals some constant number of instructions plus t of n minus d, where d is a constant, this is actually equal to c times n divided by d, okay, which is order n. So if you're only removing or reducing your problem by a constant number of items at each point, then your recursion is order n. So, questions about that? Anyone have questions on that one? Okay. So I probably will have a question about that on the final. So make sure that you really do understand that. That's a good one to have, as I said, on the final. So what I'm going to do now is start reviewing for the final. Just again to make sure everyone knows the final is week from tomorrow, May 1st. from 10:15 to 12:15. If you can't make it for some reason, let me know. Open note, open book, log into Zoom to start the exam. So a few minutes before 10:15, log into Zoom, and I will give you the access code for the exam, which will be on Canvas. Make sure that you have either some scrap paper handy so you can do some sketching, or digital sketching is fine too. You're going to have to scan whatever you sketch and upload it to Canvas as a PDF or a JPEG. And if you're curious what kind of sketching you're likely to be doing, let's just go and look at a sample final from the past. And so here, question, show the binary search tree that results of 300 is deleted from the tree below. I guarantee you there'll be a question like this on the final. And unless you're into ASCII art, by the way, I'm fine if you want to answer using ASCII art, but this takes a while. You'd probably be much more comfortable sketching the result here. So be prepared to sketch something like that. So you need to be able to sketch that. Here's another example I guarantee will be on the exam, some kind of tree rotation. So you're going to want to rotate this. Again, probably you want to sketch it. I'm fine with ASCII art if you want, as long as it's nicely done. But I will warn you, it's got to look nice. There's no guarantees that what you draw with ASCII art on Canvas is going to come up looking good on my computer. Oftentimes what happens with ASCII art is it comes up looking pretty funky. So you think it looks good, and then it kind of comes out looking like this. It's all over the place. The point I'm trying to make is it ends up all over the place. And your instructor is left wondering what the heck you meant for it to really look like. Okay, I'm just telling you that's what ASCII art often looks like if you're not careful. So you probably are going to want to be drawing. Here's another example where you'll probably want to draw. So you have an AVL tree, and I've inserted 12 into this AVL tree, and of course it's unbalanced. So identifying the bottommost node and explaining it, that would be an essay question. But, and in order to rebalance the tree, do we have to use a zigzag or zigzag case justify your answer? You would do that as an essay. But then use the proper rotations to rebalance the above tree. Again, you're going to have to do some sketching on that. So those are where you're going to have to do sketching. Deletion from a binary search tree, rotations, and rebalancing AVL trees that I've either deleted from or inserted into and are now unbalanced. So I guarantee you're going to have to do at least 3 or 4 sketching operations on the final. So make sure you have something like that. Then I know actually what I'm doing now is first reviewing instead of the second midterm. I'm reviewing the stuff we did with trees and recursion. So I'm just doing that first rather than last. You can see here I have some big O running times, and I will have you do that again because on the second midterm there was a lot of issues with that. So we'll go over that when we hit the second midterm, but I'll guarantee you some big O, some functions where I give you t of n and then you give me the big O running times. And I'll ask you which of them you would prefer. Then I will give you some code and ask you to do some algorithm analysis on it. So here I want the big O running time, and the only way to get the big O running time is to calculate t of n. And remember, I guarantee you some kind of recursion. I will probably use recursion on the final, but here was a for loop that was having the input at each step. And the correct answer for that would have been order n log n for, well, in that case, it's C. So the answer to C would have been log n. But I'm going to give you a recursive function on the final, guaranteed. So you better be able to analyze it. And then here's the scenarios. So you're going to have a scenario situation like this. So guaranteed you'll have a question like that. And there won't be anything with B trees. We didn't cover B trees in the course, so don't worry about this question. So to recap, with trees, guarantee you a question where you're deleting from a binary search tree. So like number 1. A question where you're doing a rotate about some node, question 2. And then some questions about ABL trees where I either have inserted or deleted in an ABL tree. It violates, I'm guaranteeing you it's going to violate the ABL condition, and you're going to have to do some rebalancing of the tree. And then guaranteed a question with running times, big O running times, where I give you t of n and probably ask you to order them from fastest to slowest. Then one where I give you some code and you have to analyze that code and tell me its running time. So those are the things that we've kind of covered since midterm 2 that we're going to cover on the final exam. And then, like I said, guarantee question where I give you some scenarios and you give me what the best data structure to use is. Also, it's possible, I won't rule it out, that I will give you some operations from different data structures that we've looked at this semester, and I'll be asking for their big O running times, average case and worst case. So I might or might not, because I can't overwhelm you with questions. So there could be a question that looks like 7, but I don't know. The other ones are guaranteed. And then there's going to be a coding question, just one coding question. And it's going to be a recursion, guaranteed. Now you can see in the sample one, it was a recursion involving palindromes. So you could be pretty confident I will not ask you one involving palindromes. And the other one, I'm only asking you to do one coding question on this final, but this sample final shows you which of the 2 types you will get. You'll either get a recursion that is kind of just a normal recursion like you did with the enumerate in lab 9. I asked you for a string of 0s and 1s with a certain number of 1s. Here's one with palindrome. So if you're looking for a couple examples of that kind of recursion, those are good to look at. Or it could be something like you see here, where it's going to be some kind of traversal on a tree. So here it was asking for the number of nodes in the tree. If you're looking for some other examples, in the lab, you were asked to do a recursive function for tree height, and you were asked to do a recursive function for tree find. So those are some examples you can look at that have to do with tree traversal. Now, the other thing, I'm just going to look at Dr. Plank's old 2019 final. And he had you do a tree traversal on a more generalized tree. And you should be prepared to do a tree traversal on a more generalized tree too. It would still be a tree, it's just it'd have more than 2 children. So you have to be able to just in general do a traversal on trees. What he was doing was having you find, I believe, the node with the maximum number of children. Okay, so questions about what we've covered, about questions that might involve stuff we've covered since midterm 2. Okay. That case, let's move on to midterm 2, and I'm only going to cover the stuff that really is germane to the final. By the way, in terms of prepping, make sure you look obviously at midterm 2. I've posted the midterm 2 and the answers to the coding questions and the solutions. Obviously, the sample final from the past. Also, make sure that you take a look at those exercises that I had you do in class. I have links to them. Those are good exercises to look at too. And Dr. Plank's final is something that's good to look at. His questions tend to be a bit tougher than mine. So don't feel overwhelmed by him. As I said, he tends to have somewhat tougher coding questions than I do, but still it can't hurt to look at his coding questions. And I just got a question, is the final open note, open book? Yes, it is. It is open note, open book. You will not be using the Respondus lockdown browser for the final. Okay. So let's then move into, oh, got a couple more questions before that. Okay, got it. I understand, not a lot of fans of the lockdown browser. So, yep, it's just make sure you don't work with someone else. That bad. Okay, so let's look at now midterm 2 and go through some of the questions that were most problematic, and hence I will be giving you another question about them. So first of all, I gave you a bunch of scenarios and asked you to tell me what was the best data structure. So the first question said, whoops, this isn't it. This is it. Okay. No. Just a second. Ah, that's the coding. Sorry. There we go. So the first question was, you want to keep a collection of appointments that were keyed by date time, and that you have a way to compare date times using the relational operators, and the number of appointments is typically greater than 100. It's important to be able to sort them in sorted order. So for this one, the best answer was going to be a map. And I think for some reason I put down vector. I'm going to have to check that, but if I did, you'll get points back. But the best answer here is a map. The reason is you have to be able to compare the date time somehow. So you're not going to be able to use a vector, because there's probably no easy way to map the date times to an index, you're probably using a string or some other thing, and you have to keep it in sorted order, which eliminates a hash table. So the best you can do in this case is going to be order log n for insert, deletes, and finds. So the answer is a map. So my next question was, you're keeping a census of the number of people in each state. The states are keyed by the name of the state, i.e. a string, and the states do not need to be kept in sorted order. So since you're using a string, you're not really going to be able to map that to an index, so you can't use a vector easily. You don't have to keep them in sorted order. You're just going to have to be able to efficiently locate a state and add or subtract, which means you're doing insert and find. In fact, all you're really doing is find. Hash table is good for that because it's constant time. That's better than a map, which is log n. So then I changed it up and said, okay, again, you're keeping that census, but now the state names are an enumerated constant. This is a game changer. Okay, now that they're an enumerated, now that they're an enumerated constants are integers. And enumerated constants are going to be from 0 to 1. Not 0 to 1. Enumerated constants are going to be from 0 to 49. So now a vector is perfect. A vector is faster than a hash table. You can immediately find the right index in the vector. And so you're going to use a vector for this. It is easily better than a hash table because you don't have to do a computation on the key. Okay, looks like I have a question. Okay, the question was why I can't use a vector for the second question. So why I can't use a vector here. The reason is here, the name of the state is a string. So I can't, there's no way I can quickly convert a string to an index other than by running a hash function over it. Okay, so there's no, I can't just take a string. It's going to be something like, just a moment. It's going to be something like, say, Tennessee or Georgia, and I can't map that to a string between 0 and 49 without looking, like I could do a comparison. I could say if, string, if state equal Tennessee, index equals 0, else if state equals Georgia, but that's a linear search. I'm going to have to do 50 comparisons. That's order n. That's no good. Okay, I'd have to do 50 comparisons. That would be order n. So the best I can do there is to run a hash function over that key and convert it to an index. So I can't use a vector there efficiently. Okay. So moving on, we have an internet router holds a collection of packets in a queue. Packets are added at the end of the queue when they arrive and removed from the front of the queue when they are dispatched to another router. This is the textbook case for a DQ. DQs efficiently are able to add or remove things from the front or back of a queue. So this is the classic case for using a DQ. Then a bank keeps a set of transactions for a user. The transactions are ordered by date, so there may be multiple transactions on the same date. We want to be able to efficiently add, delete, and find transactions, print out all transactions on a given date, and critically print out all transactions in a given date range, which means they're going to have to be kept in sorted order. Okay, so this right here, this restriction, this means since they're printed out in a given date range, okay, must be kept in sorted order. By date. Okay, and there's multiple per date. Okay, again, a date is probably going to be something like 2019-10-03, so there's no easy way to map that into a vector. I have to keep it in sorted order, so a hash table is out. Because there are multiple transactions per day, a map isn't as good of a choice here as a multi-map. A multi-map allows me to keep multiple ones for each date. And it will keep them sorted by date. So what I was looking there was for a multi-map. Then we add a data structure that is used to store items in a checkout cart. At an e-commerce site, the items can be in any order, so we're not keeping them sorted. Items are added at the end of the cart, but it should be possible to easily delete items from the middle of the cart. Also importantly, there are only a few items in the cart, making this perfect for a list, because you can easily delete items from the middle of a list. If all we were doing was adding items from the end at the end of the cart and removing from the end of the cart, I would have said you should use a vector, because vectors are very efficient for adding at the end and removing at the end. But because we needed to be able to delete from the middle, we wanted to use a list. Okay, and finally, the data structure you could use to store the number of times a person has visited a website, and you want to efficiently find, insert, and delete people. You do not need to keep them in sorted order. This is a classic use case for a hash table. Okay, because the person presumably that is keyed on a name, and that can't be converted directly to an index except via a hash key or hash function. Hash tables are faster than maps, so you use a hash table here. So any questions about this? Like I said, I forget now whether I said this was a vector on the test. I think I said it was a map, but if I said it was a vector, I'm going to go back and give back points, but I'm pretty sure I said it was a map. Okay, doesn't look like I have questions, so I'm going to continue. So on this one, as I said, I had to throw this question out, but it's important because this is exactly the kind of situation that you have to deal with, where depending on the input size, you could reasonably use one of three types of data structures. In this case, you had a collection of activities, and it is a so Taylor, yeah, I know that on Canvas it said that it's a vector, but I remember that I saw that and saw that it was incorrect. And I'm pretty sure I went back and gave credit for it being a map. That's what I meant, is that I think originally I had it as a vector and it was incorrectly scored, and I'm pretty sure I went back and correctly scored it as a map. So I think everyone has already gotten points for that, even though it's shown incorrectly on Canvas. In fact, I fixed it, and I think Canvas is being stubborn and won't allow me to change the solution, which is really annoying. Okay, so you could have one of three ones here, and it turned out that for small items, a list is best. For medium, it's a map. And for large, it was a vector. Now, what I was hoping for is that you would realize is that you're no longer keeping this collection of activities for dates. You're only keeping it for a day, and therefore it's ordered by start time of the event. And I was hoping that what you could realize is that times can be, they go from, yes, they can, you can say that it's something like, you may say 12 p.m. or 12:03 p.m., but what I was hoping you'd realize is you can convert times to military time. Military time does like 0100 or 1240, and those things can be very quickly and easily converted to an index. You just have a quanta of time. Most calendars have quantas like in 5-minute intervals, 10-minute intervals, 15-minute intervals. So just divide military time by, say, 5 or 10 or whatever your time quanta is, and you immediately have an index, which is what I was hoping you'd realize, but I think only 1 or 2 people realized that this is what you could do. And instead, almost all of you treated a vector as a list, which you should never use a vector in that case. It doesn't matter whether it's small, medium, or large. A vector would always be beaten by a list in this case. So there's really no reason to use a vector. So at any rate, I threw it out because I was hoping you could see that a vector could be used like this. In general, anytime a key is numeric, if there's a way to map that key into a vector index, a vector is going to be potentially a winner. So here, the reason I asked for both space and time is that vectors would be winners for very large numbers of data because they would be relatively full. So I asked you for an analysis based on both space and time. So if you're looking at space by itself, a map, if you look at a node, a map has space for a key, a value, and 2 pointers. So that's 4 items. A list has something for a key, a value. I'm sorry, it doesn't have something for a key. It's typically just a value and 2 pointers, a forward and back pointer. So maps effectively has 4 fields. A list has 3, so a list is slightly better. A vector has only a value. The key is implicit in the index, and there's no forward or back pointer. So actually, a vector takes up the least amount of space for a single entry. The only issue is that a vector needs to have 1 entry for every time quanta. So for example, if you are mapping over 12 hours, that's 1200, and you're doing it in 5-minute intervals, you're going to need 12 per hours or 144. Okay, if you have only on average, say, 5 activities in those 12 hours, that's a big waste of space. Whereas a list would, and a map would only need 5 entries. In that case, a vector would need 144. So a vector would not be as good in this case. But if the, let's say there was 50 activities on average, this is like a CEO who's really busy, now the vector is a winner because it's only got 1 value per or field per entry, and a list has 3. 50 times 3 is 150. That's already greater than 144. So a vector is actually a space winner if the number of entries, if the number of activities on average is greater than 1/3 of the available time slots. So this is the kind of analysis I was looking for, but unfortunately I didn't get it. But that's why I wanted to go over it, because this is the kind of analysis you need to be making. The other thing is that I got a lot of things like a map is more efficient than a list without any justification of that. What I need is big O justification. The reason a map is more efficient than a list is because a map has order log n and a list is order n. So you need to give me a justification for why a map is more efficient. That's the reason, is that a map has order log n, find, insert, delete, and a list is order n. So I didn't like it when you just said a map is more efficient than a list. Why is it more efficient? I need to hear about big O. So when you're comparing algorithms for time, big O is the currency of the realm, so to speak. You need to justify your answers by giving me big O. Okay, moving on. Y'all did well on the Coke processing lab. You realized that, almost all of you realized you would seg fault, because if you tried to do your search right here, you realize that these iterators might be pointing to effectively null values, so you'd get a seg fault in lines 3 and 4. So I'm not going to go over that. Question 4 did trip some of you up. So in question 4, I allocated a couple person nodes. Okay, so I allocated a couple person nodes. So I set X and I made it point to a person node. And then I set Y and I made it point to a person node. And then I made new node point to a person node. Then I made X point to this new node, thus losing the pointer here. And then I made Y point to new node, thus losing the pointer. And the problem is, these are now memory leaks. Okay, we no longer have pointers to these two objects. Okay, so that was the problem. I did say, some of you said, well, the solution is not to make X and Y point to new node, but I told you the code executes properly. Okay, I said the code executes correctly and has the intended effect of making X and Y point to new node. So the X and Y correctly pointed to new node. The problem was this memory leak. And the problem is you never use these objects. So the solution was to never create those objects in the first place. So what I wanted was that you simply did not create these objects. Whoops, it was fine to create, that's not quite right. So the solution is simply not to create these objects. Just declare X and Y, but don't assign anything to them because you initialize them down here. Okay, so that's really important. You don't want to waste time by unnecessarily allocating these objects, and then you don't want to create a memory leak. Okay. Questions about that? Okay. Looks like we don't have any questions, so moving on. So most of you did pretty well on question 5, but there was still a couple issues. First of all, some of you were writing down things like for A, you would say, okay, the running time is order 3n cubed. Okay, that's not really right. We don't include constants. We just say order n cubed. So we don't include constants. And some of you would write order n cubed plus n. That's also not right because we don't include lower order terms. So big O excludes the constants and it excludes lower order terms. The other issue here was some of you were saying that the running time of A was less than the running time of B, despite the fact that as n goes to infinity, T of n, so A, its running time as n goes to infinity is 3n cubed, and the running time of B as it goes to infinity is just n cubed. So that's B and that's A as n approaches infinity. 3n cubed is greater than n cubed. Okay, still as n goes to infinity, 3n cubed is still 3 times slower than n cubed. So in fact, the answer was B is less than A. But many of you seem to think A was less than B, which is incorrect. The other issue is that many of you seem to think that 2 to the n is less than n cubed. It's not true. Okay, 2 to the n is greater than n to the 100th power. It's greater than n to 1,000. 2 to the n grows incredibly rapidly. 2 to the n is always greater than n to the x, where x is fixed. Okay, exponential. This is called exponential. And this is called polynomial time. Polynomial time is always faster than exponential. Okay, polynomial time is always faster than exponential as n approaches infinity. And that's what I said. As n approaches infinity, order the algorithms from fastest to slowest. Also, some of you ranked this constant time as being very slow, but as n approaches infinity, this one stays constant and all the other ones run past it. So constant time is always the fastest as n approaches infinity, no matter how big this constant is. I know this constant was huge, but nonetheless, as n approaches infinity, eventually all of them run past it. Even log n eventually run past this. As n approaches infinity, it gets bigger than this big value here. Okay, so the key was, I said, as n approaches infinity. Okay, on number 6, I'm not going to have a, oh, I have a quick question. Okay, it says, can you show the big O for part C? For part C right here, the big O was ordered 2 to the n, because 2 to the n, again, is much, much greater than n log n. Okay, n log n is, if you're looking for where it is n is less than n log n, which is less than n squared. Okay, so 2 to the n is much, much greater than n log n. So you say it's order 2 to the n. And for h, you say it is order 1.6 to the n. Okay, so for number 6, most of you got it except for 2 of them. Actually, except for 1. The only one that gave most of you issues here was this one, tree house equals bear house. So I gave you 5 different things. It was 3 constructors, a destructor, and an assignment operator. The only one that really went badly was this one. This is not an assignment. Most of you said this was an assignment operator. It's not. This is a declaration of a variable. You are declaring this variable, and this calls the copy constructor. So 2 and 3 are identical here. Okay, this statement right here, when you're declaring something, is identical to saying tree house of bear house. It calls the copy constructor. So that's really important, because I know it looks like it's an assignment operation, but it's not. It's an initialization operation. This is an initialization operation. Not an assignment operation. Okay, 5 was an assignment operation. That was an assignment operation because no declaration was happening there. So pretty much that was the only issue with that question. On number 7, many of you got this, but there was a few issues. So this was mystery. And what you were doing was you were doing stack frames. So we started and we were at main. And we were at line 1 in main. And it calls mystery with 53. And n is equal to 53 here. So 53, if you do the computations, you end up with 53 being an odd number. So you're going to call mystery of 50. So you're at line 5, and you're going to call mystery recursively with n equals 50. Okay, because 53 minus 3 is 50. So you're going to call mystery with n equals 50, and in that one, you're going to be at line 4 because n is even, 50 mod 2 is even, so you're going to be at line 4, and you're going to call mystery with n equals 25, which is going to put you at line 5 because n is odd, and you're going to end up calling mystery with n equals 22 because 25 minus 3 is 22. And you're going to end up at line 4. And I'm now going to jump ahead. You're going to end up with n equals 11. Then you're going to end up with n equals 8. Then you're going to end up with n equals 4. And finally, you're going to end up with n equals 2, which is the base case. So when n is equal to 2, you're going to come into mystery. And you're going to execute line 3 because n is equal to 2. So that's your base case where you end, and you're just going to have one thing, which is line 3. Now, many of you had 2 stack frames at the end. Many of you at the very end had mystery, and you had n equals 2, and for some reason you had line 4. But you never get to line 4 if n is equal to 2 because it will terminate at line 3, returning 4. So this would never happen because you could never get to line 4. Instead, you would get to line 3 and you would exit. Now on the final, so I might give you a stack frame question like this on the final as well, because there was a myriad of issues associated with this. So any questions about how I derive these stack frames? Okay, I'm going to run over by just a couple minutes because I want to get to Diamond Hunt and the list. I'm going to run over by about 5 minutes. And I'll do the coding. What I'm going to do with the coding questions, I'll do a separate video with those and post it so that you can look at the coding questions. So I'll get that posted probably tomorrow. With Diamond Hunt, you're a diamond hunter. You're looking for diamonds in the mine. So actually, I'm just going to go to the solution for this one. So the solution for the diamond case was, the base case is it doesn't have a diamond. So you keep searching until you reach a string that does not have a diamond. Many of you said the base case was where the string either had 0 or 1 characters, and that's true, but it's incomplete. Okay, it's definitely the case if it has empty string or 1 character that it can't have a diamond. But in general, any string that does not have a diamond in it has a diamond count of 0, and that was the base case. So then the recursive case was any string that had a diamond, and what you did was you removed the diamond from the string to give you a so-called residual mind. You called the function recursively on this residual string, and you added 1 to that amount. So your diamond count is 1, plus the number of diamonds returned by recursively processing the residual mine that is obtained by deleting the first substring of the form of a diamond. So that is what I wanted, was that you removed one diamond from the string, so you added 1 to your diamond count, and you then recursively called it on that residual string. Okay, and then the final one, this won't be on the final, but nonetheless, this was very widely missed, so you still need to know it. What I did was I pushed hair onto a list on the front, then I pushed bear onto the back, then I pushed hen onto the front, and then I pushed rabbit onto the front. So I had a list that looked like this when I was through these. Whoops, I'm sorry. I have hare pushed back. And I missed hound. Hound got pushed on. Right there, hound got pushed on. So when I was done with these first 5 things, I had this list. Then I set knit to be the begin, and I incremented it 3 times. 1, 2, 3. So it pointed to bear. And then I did an insert of grizzly. So grizzly came in here. Before bear. And knit was set to whatever the insert returns. So now knit pointed to grizzly. So at this point, knit pointed to grizzly. So now I decremented knit twice. So I decremented it twice, and knit now pointed to hen. Whoops, grizzly is still in there. Don't want to get rid of grizzly. So grizzly is right here, but knit points to hen, and I now deleted hen. So hen was removed from the list, and knit now pointed to hare. Because it always points, when you come back from a delete, it points to the item after the deleted item. So in this case, it pointed to hare because that's the item after the deleted item. Then I set rknit to be equal to rnames.begin. So rknit pointed to hound, and I incremented rknit twice, once, twice, so it pointed to grizzly. And then I set knit1 to names.end, so that's out here. It points to the, knit1 points to the Sentinel node. And finally, I set rknit1 to names.begin. That's the, whoops, don't want to get that wrong. Doesn't point there. It points to hound because rknit1.begin points to the end of the list at that point, which is hound. So that's where those 4 pointers point at. Okay, so I will see you May 1st at 10:15 a.m. in here for 2 hours. And I will go over the coding portion of the exam in a separate video. Make sure you look at that, because I might decide to do something with lists or maps just as part of the coding question involving recursion. So you still need to have, or I might do something with maps and lists as a pointer problem. So I might have you look at some code fragments and tell me something about how that list or map was working. So in fact, I know I just said you can't expect a problem like this, but now that I'm thinking about it, you might expect a problem like this. So you need to be looking at it and prepared for a problem like this as well on the final. Okay, I'll be around for a couple minutes for questions. I do have a class at 12:40. I have office hours today from 2 to 3. So if you can't get the question answered, then you can get it answered at that time. And